right, now let's recall what we talked about in the previous lecture. So the setup is you have V and W subspaces of Rn and Rm respectively. Okay. And suppose you have a linear transformation T from V to W. Linear transformation. Okay. And if I have a basis, let's see what the notations were. If I have a basis V1 through VR, with V basis, then for every V in V, oops, not that, V in V, we can write V as a linear combination of the basis vectors. So A1 V1 plus A2 V2 plus AR VR. Then the point is T of V is equal to T of A1 V1 plus A2 V2 plus so on, plus AR VR, which now if you use linearity requirement, this is equal to A1 T of V1, A2 T of V2, plus so on, AR T of VR. Okay, so to describe T, it's enough to describe T of V1, T of V2, T of VR. So in words, if you want to describe a linear transformation, what you need to do is to describe its effect on a basis vectors. Okay, so in particular, if T is of this form, from Rn to Rm, and we consider what we call the standard basis, E1, E2 up to En of Rn, okay, then X if you have a vector in Rn, say called X, it's going to look like this. It's a column vector with entries x1 through xn. And this is written as x1 E1, x2 E2, plus up to xn En, right? And T of x is the following. T of x1 E1 plus x2 E2 plus stuff plus xn En. So again, by the property of being a linear transformation, this is x1 T of E1, x2 T of E2, and so on, xn T of En. Okay. Now, if we let A to be the matrix with columns TE1, TE2, and so on to TEN. And these guys are columns. Then, and this, I mean, this is equal to the matrix A times the vector X. Okay. So, in other words, we can describe T using the matrix A, and the way the T acts on vector X is given by the matrix multiplication of A with X. Okay, so yeah, so that's something we may use from time to time. Okay, this shows a close relationship between matrices and the linear transformations. Okay, so now let's move on to some further definitions. So given, again the setup is you have two subspaces, E and W, and you have a linear transformation T from V to W. Okay, and we define the null space or kernel of T is N of T, which is by definition the collection of vectors B in V, so that T of V is the zero vector. This is by definition a subset of V. The range of T is denoted by R of T, which is defined to be the collection of vectors W in W, so that W is equal to T of V for some V in V. And this is by definition a subset of W. Okay. Now, it's an easy theorem to check that the null space and the range are subspaces. Okay. And the proof is straightforward. Let's do this for n of the null space first. What do we need? In order to be a subspace, you need to have the zero vector. You need closure on the addition and scalar multiplication, right? So first thing is 0 is in n of T, because T of 0 is always 0, and this requires a little bit of a proof, and we should actually check these on the side. let's see. T of 0 is equal to T of V minus V, right? For any V, you have the, or maybe we should write it slightly more formally, plus the additive inverse, right? V plus its additive inverse is 0. Now, being linear means it's TV plus T of negative V. Now, we proved this before, that negative V is minus 1 times V. Okay. And now we can pull out this minus 1. So we get T of V plus minus 1 times T of V, which is T of V minus T of V, which is 0. Okay, so that proves that the range has the 0 vector. Sorry, that the null space has the 0 vector. Now the next thing is, if you have V1, V2, both in the null space of T, then this means that T of V1 is 0 as well as T of V2. Then you can check, I mean, if you want to know whether V1 plus V2 is in N of T or not, and for that you compute T of V1 plus V2, which by linearity is T of V1 plus T of V2, which is then equal to 0 plus 0, therefore 0. So this shows that V1 plus V2 belongs to the null space. And finally, if you have a vector in N of T, the null space, if you have a scalar A, then we know that T of V is 0 because by the requirement that V belongs to the null space. And then what this means is that when you try to compute T of AV, this is by linearity A times T of V, which is A times 0. And we know any number, any scalar times the 0 vector is the 0 vector. So T of AV is 0. So AV belongs to the null space. And these three properties together tells us that the null space N of T is a subspace. Okay. Now for the range, we proceed in a similar fashion. Right, we need to check three things. First of all, the range contains the 0 vector of W. And that is because if you want the 0 vector to be in the range, it means it has to be of the form T of something. And that something is 0. And as we've already seen over here. Okay. Now, the next property, if you have W1, W2 belonging to W, no, I want W1, W2 from the range, then this means that W1 is equal to T of V1, W2 is equal to T of V2 for some V1, V2 belonging to V. Then we want to consider W1 plus W2. That is equal to T of V1 plus T of V2. So that is by linearity again, V1, T of V1 plus V2. So therefore, this belongs to the range of T, because W1 plus W2 is of the form T of something. Okay, and finally, if you have W in the range of T and a scalar A, this means that W is of the form T of something called V, or some V in V. Then A times W is A times T of V, which again by linearity is T of AV. This now belongs to the range. Anything of the form T of something belongs to the range. And so the three required properties for being a subspace holds for the range. Therefore, it's fine. Now remark. Okay. As we've seen above, if we have our linear transformation like these, from Rn to Rm, then we can find then T of x is equal to the matrix A times x for some A, some matrix, some A n by n matrix, as we constructed before. In this case, the null space of T is the same as the null space of the matrix A that we defined before. The range of T is the same as the range of A that we defined before. Okay. All right. And furthermore, there's the following fact that we can consider the dimension of the null space of T plus the dimension of the range of T is equal to n. And we're now going to prove this fact for now. But yeah, so this is something that you can check in every example. So these quantities have names. Also, this is called the rank of T, and this is called the nullity of T. Nullity of T. This is called the rank of T. Okay. All right. Now with this remark understood, if we are asked to determine the range and the null space, it's something that we've seen before, right? If we are given a linear transformation like these, so let's write it down. If we are given a linear transformation like these, we can find the matrix A so that T of x is equal to A of x for every x, and work with A to determine the null space of A, the null space of T, which is just the null space of A, and the range of T, which is the range of A. Okay, the null space, to determine the null space amounts to solving a linear system. To determine the range, well, we've seen this before, right? There are a couple of different ways to do it, but again, this is meant to just tell you that the question for linear transformations is reduced back to the same question for matrices. Okay, let's see here. Now let's consider something special for linear transformation. Let's call a definition here. Say a linear transformation from R2 to R2. Okay, is called orthogonal if T of V has length equal to V for every V in R2. Okay. There are different names for this. This is also known as an isometry. Okay. And we're going to think about an easy fact here. Our theorem T R2 to itself is orthogonal if and only if, for every V and W, or U and V, U and V belonging to R2, we have TU dot TV equaling U dot V. Okay. All right, so proof of this. So first of all, this sort of this theorem here somehow makes the name orthogonal a bit more sense, because being orthogonal is defined using using dot product, and this equation here just means that the transformation T preserves the dot product. So if two vectors were orthogonal to each other, the images under T will still be orthogonal to each other. And for this reason, it makes sense to call T an orthogonal transformation. Okay, so now let's prove this. So there are two implications. The backward implication assumes if Tu dot TV is equal to U dot V for every U and V in R2, then TV, let's do the case where U and V are equal. TV dot TV is equal to V dot V, right? V dot V is the square of the length of V. TV dot TV is the square of the length of TV. So TV has length equal to the length of V for every V in R2. Okay, so that's straightforward. Now the backward implication works as this. Suppose TV has length equal to the length of V for every V. Now we want to argue that tu dot dv is the same as u dot v, right? So for u and v in R2, we then have the length of t of u plus v equals to the length of u plus v. Okay. And this is just because t is assumed orthogonal, so t of any vector has length equal to the length of that vector. So in particular, we have t of u plus v has length equal to the length of u plus v. And we can square these two things. And that will give us t of u plus v dot t of u plus v equal to u plus v dot u plus v. Now this is something we can further compute because t of u plus v is t of u plus t of v. And likewise for the other part, t of u plus t of v. And this is the right hand side is still u plus v dot u plus v. Now we can expand the dot product. We get u dot u plus u dot v plus v dot u plus v dot v on the right hand side. On the left hand side, we have t of u dot t of u plus t of u dot t of v plus t of v dot t of u plus t of v dot t of v equaling that. Now we can rewrite this as follows. T of u dot t of u is the square of the length of tu, and t of u dot t of v is the same as t of v dot t of u, so there are just two copies of that. Copies of t of u dot t of v. And similarly, t of u dot t of v dot t of v is the square of the length of t of v. Now for the right hand side, u dot u is the square of length of u. U dot v and v dot u are equal. V dot v is the square of the length of v. So like that. Now the square of t of u, the square of the length of t of u is equal to the square of the length of u, because the length of t of u is the same as the length of u by assumption. So and likewise, the square of the length of the t of v is the same as the square of the length of v. So these two terms pairwise cancel each other. We're left with 2 times t of u dot t of v equaling 2 times u dot v, which is what we want to prove. And what we want to prove is t of u dot t of v is u dot v. What we prove is twice of that, but we can divide by 2. So that's no big a deal. Okay. All right, so this theorem here is meant to tell you, meant to justify the use of terminology orthogonal here, because the condition which was the defining condition is on the length, but it really is equivalent to saying that the transformation T preserves the dot product. Hence, it preserves orthogonality. Okay, now let's look at an example, or maybe let's look at some theorem first, some general property. Okay. Yes. Oops. Okay. So let's see. Again, T goes from R to R. Sorry, R2 to R2. Is orthogonal if and only if first two things. T of E1 has length equal to 1, as well as T of E2. And second thing, T of E1 dot T of E2 should be 0. Okay. Proof. Let's see. Yeah, so how do we prove this? Forward implication. If T is orthogonal, then so if T of U has length equal to length of U for every U in R2, then T of E1 has length equal to the length of E1, which is 1. T of E2 has the length of E2, which is also 1. And as the previous theorem showed, T of E1 dot T of E2 should equal to E1 dot E2, which is 0. Okay, that's good. So now going backwards, we want to argue. What do we want to argue? We want to consider, let's say, how do we do this? We want to study how T acts on any vector, say x, x1, x2. So we're using the standard basis. So that's written, x is then written as x1 e1 plus x2 e2. So Tx, I can now compute the length of Tx, or the square of that first. That is, of course, Tx dot with Tx, which is T applied to x1 e1 plus x2 e2 dot with itself. And so now we're going to distribute this as follows. So first of all, you have x1 t e1 plus x2 t e2 dot with itself, x1 t e1 plus x2 t e2, like that. And then you compute this dot product explicitly. You get x1 square t of e1 dot with t of e1 plus, well, x1, x2 t of e1 dot t of e2 plus x2, x1 t of e2 dot t of e1 plus finally x2 square t of e2 dot t of e2. Okay, and now we can process this. Our assumption is that t of e1 dot with t of e2 is 0, so this term goes away. Likewise, this term goes away. And we're also assuming that the lengths of t of e1 and t of e2 are both 1. So these guys are 1. So therefore, we're left with the square of x1 plus the square of x2, which is the length of x squared. So And this chain of equality shows that the square of t of x, the length, is equal to the square of the length of x. So the length of t of x is equal to the length of x, which is the requirement for t to be orthogonal. Okay. All right. Finally, let's look at some examples. Let's see. Well, just one example, I guess. So consider the linear transformation defined by t of v being a times v, where a is cosine theta sine theta minus sine theta cosine theta. Theta is some real number. Okay. And let's check that this is indeed an orthogonal transformation. And we can use the theorem, right? T is orthogonal. To use the theorem, we want to compute the length of t of E1 and the length of t of E2, and as well as the dot product TE1 dot TE2. Okay, so that we need to compute these things. Really what this means is that we need to compute TE1 and TE2. T of E1 is A times E1, so that's the column vector cosine theta, sine theta. T of E2 is the other column, negative sine theta, cosine theta. Okay, so then to compute the lengths of these vectors, we dot it with themselves. So TE1 dot TE1 is just cosine square plus sine square, which is equal to 1. TE2 dot with itself is, well, sine square plus cosine square still equals to 1. Okay. Yes. Finally, T of E1 dot T of E2 is, well, cosine theta, negative sine theta, plus sine theta, cosine theta, that's 0. So, and remember what we need these two vectors to have length 1, and this dot product between them to be 0. And that's all checked out here. Okay, so T is indeed orthogonal. Let's see here. And we can actually give this T an interpretation as follows. So let's say we have our XY plane. This is our R2. So if I have a point AB here, right, let's say this length is R, and this angle is phi, then the use of bipolar coordinate, I know that A is R cosine phi, B is R sine phi. Okay. Now if this is my vector v, and t of v, which is a times v, is let's decide to call the answer CD, then C is equal to what? Well, sorry, this A is cosine theta, sine theta, minus sine theta, cosine theta, AB. Right, so you can, from here, compute C. C is A cosine theta minus B sine theta, right? I remember what A and B are. A is R cosine phi, so R cosine phi cosine theta, minus B is R sine phi, so R sine phi sine theta, and the angle, the sum formula for cosine theta tells you that this is R cosine phi plus theta. And for D is A sine theta plus B cosine theta. And again, A is R cosine phi sine theta plus B is R sine phi cosine theta. So again, there's a sum formula for sine that tells you that this is R sine phi plus theta. So what is this point CD? This point CD is the image of the point V under the transformation T. And according to this description, the x coordinate is R cosine theta phi plus theta. Y coordinate is R sine phi plus theta. If you use the polar coordinate to describe things, you see that this is how you get CD. This angle here being theta, the length is still R. So you basically rotate counterclockwise by the amount theta. So what this is telling us is that T is the counterclockwise rotation by an angle theta. Okay. Good. Now let's see. So, okay. So one more thing. Now, as a remark, again, let's say you have a transformation, a linear transformation that is orthogonal. Suppose T is given by the matrix, right? As we've seen before, for some 2 by 2 matrix. Okay. Then, as we've seen, T of U dot with T of V is equal to U dot V, as we proved before. And now in terms of the matrix A, what this means is that AU dot AV is equal to U dot V. Okay. Now, as you remember, you can use matrix multiplication to write dot product. So if we do that, we will be writing transpose of AU times AV equals to transpose of U times V. Now transposition has the property that if you transpose AU, it's U transpose times A transpose. And then you can group these products together like that. This is true. So you have U transpose A transpose A, V equal to U transpose V. And this is true for every UV. If you take U equal to E1, E2, and V equals to E1, E2, there are then four pairs of such UV. Then we'll get A transpose A actually equals the identity, 2 by 2 identity. Okay, conversely, if A transpose A is equal to the 2 by 2 identity, then reversing the argument I just did, we get that AU dot AV is U dot V. So the statement is that T is orthogonal if and only if the corresponding matrix A satisfies these property, A dot transpose A is equal to the identity. Okay? And you can check that this is indeed true for the rotation matrix we've seen up here. Okay, so that's this lecture.